Obtain the mesh file and also the full training movie by purchasing this product.
In this project, we will numerically simulate the electrochemical process which happened inside a fuel cell using ANSYS Fluent software. A fuel cell is an electrochemical cell that converts the chemical energy of a fuel, often hydrogen, and an oxidizing agent, often oxygen, into electricity through a pair of redox reactions. Fuel cells are different from most of the batteries in requiring a continuous source of fuel and oxygen to sustain the chemical reaction. Fuel cells can produce electricity continuously for as long as fuel and oxygen are supplied. The fuel cell used in this simulation is a type of polymer electrolyte member fuel cell. The model consists of two main cathode and anode segments, each of which has 4 layers, including a flow collector, a flow channel, a gas distribution area, and a catalytic section, and the space between the anode and cathode layers are filled by the polymer membrane. In addition, since in fuel cell modeling various types of gases react, the species transport module is also automatically activated in the simulation. The hydrogen gas enters the anodic channel inlet and the oxygen species enter the cathodic channel inlet to allow the corresponding reaction to occur in the fuel cell, and the polymer membrane is the pathway for the gas species to pass through. Flow collectors are made of solid material with thermal energy sources and electrical potential. The flow channels carry a mixture of gaseous species including oxygen and hydrogen and water. The catalytic part consists of a porous medium with a porosity coefficient of 0.5 and contains mass sources: thermal energy, electrical potential, proton potential, saturated water, hydrogen, oxygen, and water. The gaseous diffusion zone comprises of a porous medium with a porosity coefficient of 0.5 and contains the mass sources: thermal energy, electrical potential, saturated water and hydrogen, oxygen, and water gaseous species. The polymer membrane region also consists of a porous medium with a porosity coefficient of 0.5 and has thermal energy sources and proton potentials. Also, since the water content within the model must be 0, a fixed value is used to define the value of water equal to 0. The purpose of this study is to investigate the fluid behavior and thermal conductivity of a polymer fuel cell and its effect on the mass fraction of gaseous species and the amount of electricity produced in the cell. The three-dimensional geometry of the present model is designed by Design Modeler software. The present model has a symmetrical structure and consists of 9 regions of 7 specific fluid zones, including cathode and anode flow channel, cathode and anode gaseous region, cathode and anode catalytic domain, and polymeric membrane, as well as 2 solid zones. The solid zone consists of a cathodic and anodic current collector. The mesh of the present model is carried out by ANSYS meshing software. The mesh tab is structured and the element number is 142,000. By clicking on display button, a new window will appear which you can see different parts of your geometry. Now in the appear window, which shows you the names of the different parts of your geometry, you can click and select each part and then click on display so that the software will show you that part. As was previously mentioned about having different gaseous and chemical species in our model, you can see that by double clicking on the species, we have enabled the species transport model. Also under the mixture properties, you can click on edit button and in the appear window, change the mixture material. Also, it should be pointed out that in this intermediary window, you can see the properties of the mixture. For example, you can see that we have set the density of this mixture to abide the ideal gas law. The electrolyte header, the membrane area of the fuel cell must be defined, which is the center of the model building. In the zone section, the membrane area should be defined. And in this window, you can see that the membrane boundary is selected under the zones section. It is used to define specific fuel cells. For example, contact resistivity is used to deal with some of the cell contact surfaces. A jump in electrical potential caused by incomplete conduction. The coolant channel mode is used for cases that the cooling channel exists in the fuel cell, and the stack management mode is used when the multiple fuel cell units are combined to increase the efficiency. After expanding the fluid section under the cell zone conditions, in the appeared window you can see that the material name has been defined as FC mixture. Also, you can see that we have enabled the fixed values option. As was previously explained about the water content in our anodic and cathodic channels, you can see that under the fixed values tab, we have set the value of water content to be equal to 0. After clicking on the Porous tab, under the Fluid Porosity section, you can see that the fluid porosity has been defined to have a value of 0.5. Also, you can see that the solid material name has been defined, as you can see in this window. By clicking on Edit, a new window will appear in which you can change the settings and properties for this material. As was previously explained about the water content in our anodic and cathodic channels, you can see that under the Fixed Values tab, we have set the value of water content to be equal to 0. After clicking on the Porous tab, under the Fluid Porosity section, you can see that the fluid porosity has been defined to have a value of 0.5. Also, you can see that the solid material name has been defined, as you can see in this window. By clicking on Edit, a new window will appear in which you can change the settings and properties for this material. If you click on the Thermal tab, you can see the temperature of the fluid flow entering this boundary. By clicking on the Species tab, you can define the species mass fraction of the fluid flow entering this boundary. The most important point we should pay attention to is the gauge pressure amount, which has a value of 0, which means that the fluid flow will exit our computational domain to atmosphere. Now, under the UDS tab, under the user-defined scalar boundary condition, you can see that for electric and protonic potential, we have defined the settings of a specified value and a specified flux. Also, under the user-defined scalar boundary values, you can see that the value of 0.5 for electric potential and 0 for protonic potential for this boundary have been defined. After clicking on this boundary, you can see that under the Thermal and UDS tab, coupled condition have been defined, which means that this wall is in contact with the fluid on its both sides. After clicking on this boundary, you can see that under the Thermal and UDS tab, coupled condition have been defined, which means that this wall is in contact with the fluid on its both sides. After clicking on this wall boundary, you can see that heat flux thermal condition has been defined with a heat flux rate of 0, which means that this wall is adiabatic. And if we click on UDS tab, you can see that under the user-defined scalar boundary condition of electric and protonic potential, the setting of a specified value and a specified flux respectively have been defined. Now, as was previously mentioned about the outer boundaries, which have the electrical and protonic potential of 0, you can see that we have defined those values in this window. After double-clicking on the Residuals button, a new window will appear. In the Appeared window, you can see the absolute criteria for equations like continuity, x velocity, y velocity, and so on. Now, when you set the software to start the simulation, there would be error between each iteration. Now, if that error is less than these criterion, it conveys the meaning that that equation has reached convergence. If you expand the surfaces under the Results section, you can see that 3 different planes have been defined. By double-clicking on x-coordinate plane, in the Appeared window, you can see that a plane on x-coordinate have been defined. Now, in this contour, you can easily see how the hydrogen has a higher mass fraction in the upper channel, and after passing the membrane, which is in the middle section of this contour, you can see how the mass fraction of hydrogen has changed from its highest value to its lowest. Finally, the summary of different settings and setup that we have used in our project is presented to you in the slide.
Obtain the mesh file and also the full training movie by purchasing this product.
To benefit from Mr. CFD services including simulation, consultation, and training, contact our experts via info@mrcfd.com.